Alright, good afternoon guys. Today we're going to be going over problem set 3 for Organic Chemistry 2, Fall 2025. So let's go ahead and get started with question number 1. Give the semi-systematic name for each of the substituted benzenes shown below. So, have you guys remembered your parent names yet? I hope you said yes, because if you haven't, then you are screwed. I'm just kidding, just remember them before the exam day. So let's go ahead and get started with question number 1. In order to name this, we need to find the highest priority parent chain. And in this case, it is going to be, what sticks out to me is this benzaldehyde. Okay, so of course we do have this here. If we look here, that is a toluene group, and if we look here, this is an anisole group. But if we know the different priorities, we know that the benzaldehyde is going to take priority and automatically become carbon number 1. So if we now we have a little bit of a conundrum. We can either name going to the right or we can name going to the left. And no matter what we do, it's going to end up with a 1, 2, 6 naming pattern. So the next thing we must look at here, because the patterns are the same, is going to be alphabetical order. So if we look here, this is going to be a methyl side chain, and this thing is going to be a methoxy side chain. So in this case, this is going to come before methyl, so then we can name the parent, or I guess this molecule based off of that. So it's going to start off with 2-methoxy, and then it's going to end up going left, so this is going to be 2, this is going to be 2, 3, 4, 5, 6, and it's going to be 6-methyl. If we look at the main parent molecule, it's going to be a benzaldehyde. Okay, and remember the important thing to know here is that we don't want to do any ortho para meta nonsense. That is to designate different side chain, or I guess different chains in relation to one another. But when you're told to name something, it is very important to do the proper naming, which is using the proper numbers. So let's look at question number 2. We don't have any big parent chains sticking out, but we do have 2 side chains, and no matter which way we name it, it's going to be 1,4 if we go this way, or if we go this way, it's going to be 1,4. So the next thing we must do is obviously look at which comes alphabetically first. This is a chloro, and this is an ethyl. Last time I checked, C came before E in the alphabet, so we're gonna be naming it with chlorine being on carbon number 1. So we get 1 chloro, 4 ethyl, and benzene, because we don't have any special cases here. Awesome. Now let's look at this last one. Remember, what do we say in class a bunch of times, as well as in the previous homework episodes? We do not want this nitro group to be a parent chain. This will never ever be a parent chain. Loser. Anyway, so the important parent chain we must know here is this OME, which is anisole. Okay, since this is going to be our parent chain, this is going to be carbon number 1, and if we go naming to the left, this is going to land on carbon number 2, 3, 4, 5, as opposed to naming going to the right, we're going to end up with a 1, 3, 6 designation, so we want to use the 1, 2, 5 designation. So now let's go ahead and start naming this based off alphabeticals. We have 5 bromo, 2 nitro, anisole. Remember, that's our parent name. Awesome. Now let's look at question number 2. Each of the following alkyl chlorides can participate in a Friedel-Crafts reaction with AlCl3 and benzene. Circle all the reagents that would undergo a carbocation rearrangement. So this really requires you to know your chemistry. So let's go ahead and refresh ourselves. With a Friedel-Crafts reaction, this chlorine is going to kind of pop off, and this is going to have a positive charge here, for an example. And carbocation rearrangement can occur if and only if the adjacent carbon molecules have a higher substitution pattern, thus giving it a more stable product. So let's look here. This is a perfect example. The positive charge here is going to be on a primary carbon, but if we look right next door, boom, secondary carbon. So if we want to add this Friedel-Crafts addition, it's going to look something like this. Right? It's not going to be adding the straight chain. So in this case, this will do a rearrangement. Now let's look at the second one here. This is going to be primary, and this one right here, primary. They have the same pattern, same substitution patterns, so in this case, this will not do any rearrangement. Now let's look at the second one here. Positive charge is going to land here, and if we look right next door, this is actually going to be primary, which is even less stable, and this is going to be secondary. But because there are the two secondaries next to each other, neither one of them is really going to take priority, so this will not do any rearranging of any sort. Let's look at the one down here. Positive charge is going to land here. This is going to be a primary carbon, and the one right next door is secondary. So in this case, this is more stable, so this will rearrange. Let's look up here. This right here is secondary, and if we look right here, this is actually tertiary. So this will actually do rearrangement as well. Let's look at this final one here. This is going to be primary, and if we look right next door, this is quaternary. This is the max substitution, which is all very, very stable, and this will for sure rearrange. All right, now let's move on to second page. Draw the full arrow pushing mechanism for the chlorination of benzene with FeCl3 and the scaffold provided for each step. So we already given of what we want our starting reagents to be, and we even know what our final product is going to be. So this is really going to be about filling in the blanks, and do you know your mechanisms inside and out. Guidelines include alone pairs and not zero formal charges. Draw the resonance structure for each iridium ion following this mechanism. Use your best friend. It doesn't say that, but we know it as our best friend. Use B with a lone pair to represent a generic base if one is required, and circle the major product. So let's go ahead. Formation of the electrophile. We learned this so many times. We want to do chlorination, so we want to use Cl2. It is very important to draw out the Cl2 that looks like this. We're diatomic molecules or atoms, and it's going to be reacting with the FeCl3. So we've done this in class. We know that the electrons here are going to attack the iron right here, and what this is going to do is form this intermediate here. This is a very important intermediate that is very likely will show up on the exam because of just how important it is. Right here, right here, right here. This is going to assume a positive charge, and remember, this charge is neutral. And in this case, we have a benzene here, and this nucleophilic benzene is going to react with this chlorine right here, and what goes around must comes around. So this pair of electrons is going to jump right here on the chlorine, giving us something that looks like this. Bada bing, bada boom, bada boom, 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 boom. And we have the chlorine here, and you can draw the hydrogen here if you would like. And of course, there's going to be a positive charge, and it's also very important to know that we have our FeCl4 now kind of floating around in solution. So now we're given a couple of resonance arrows here. Just keep in mind that resonance arrows are not the same as equilibrium arrows, which are not the same as reaction arrows, which are not the same as radical arrows. Just be very careful when drawing out your arrows, because that is a very easy way to lose some points. So resonance structures, we should be pro our resonance structures now. So this has two resonance structures, and there's a deficiency in the p orbital here. This pair of electrons next door can swing over here and form a resonance structure right here. And remember, all resonance structures, only the charges move, and electrons move, but the atoms will always stay in place. This is going to move one more time. Door hinge over, swing over like that. Bada bing, bada boom. Now we have a structure that looks like this. Cl and hydrogen. Okay, and so now we have our resonance structures, and in order to get the final product here, we must use our best friend, any convenient base. We're going to draw an arrow attacking this hydrogen, and this pair of electrons right here is going to swing down here and fill in the double bonded charge, giving us this final product.